All right, so up to this point, we've used a few different predictor variables in our models, but they've all been quantitative or numeric. We have not used any type of qualitative or nominal predictor variables. All right, so what that means is all our predictors have been on a numeric scale. We haven't had to use anything that we would consider like binary or multi-level, such as eye color or the neighborhood of a home or anything like that. But we can use that kind of information. For example, let's take a look at a different data set. Here we're looking at a credit data set. And in this case, I'm just going to select two variables, the gender and then the balance. And so this is the balance. I believe the actual interpretation of this is the balance that somebody has on their credit card. Right? So basically what we're looking at is, or maybe a question we would ask is, does the gender influence the balance that somebody carries on their credit card? Well, we can do this, but the way that we do this with the model is a little bit different than when we had numeric variables. And what we actually need to do is what's called dummy encode our predictor variable. So what dummy encode means is what we're going to do is we're going to say, hey, look, we're going to label this as a 1 if the person is a female and 0 if the person is male. So behind the scenes, what R is doing is it's actually taking our gender variable and it's saying, okay, if the value is male, then I'm going to replace this with 0. If the value is female, I'm going to replace this with a 1, right? And I'll do that for each observation. Now, we don't need to actually do this. We will talk about feature engineering in a later lesson. But we could actually take this variable as it is, this gender variable, and apply a linear model just like we've done before. So here I create a model, and this is going to say this is a simple linear regression model where balance is a function of gender. And what we get for our model output is we have our intercept as usual, but then we have gender and it says female. Okay? And so what this means is that this beta naught, right? Here I say beta naught equals 510. What that means is that's the average credit card balance for our males. Okay? So what's happened now since the male observations have been coded as 0, that becomes our reference variable or reference level. And so the intercept represents the average value, the average Y value, in this case, the average balance for that reference level. So for males. So on average, males carry $510. Now, the second one, gender female, what this means is that if the observation is a female, that they tend to carry $19.7 more than the males. Okay? So what this means, if we want to get the actual average credit card balance for females, we would take 510 and then add 19.7 to get 529.7. And that's the average credit card balance for females. Now, another thing, when we're looking at this table, if we see the p-value for this level is what we consider statistically significant or very close to 0 here, then what we can actually say is that, yes, females, this difference in the average balance carried compared to males is statistically different than 0. Now, in this case, we are using male as a reference level and comparing the females to that. But that's kind of arbitrary, and what we decide to use as a reference level is completely up to us. So say we wanted to switch that and we wanted to have females as the reference level. We could do that, and all we're doing is we just change the level of the factors. So in this case, we are going to go ahead and have females be the first level. So now this intercept, when we run this model after we've changed the level order of our gender variable, Now when we run this model, what we see is the intercept is actually representing the average credit balance carried by females. And then now we see here gender male. What this means is that this negative 19.7, this is the average difference between female and male balances. So we would now say, well, the average balance for males is the intercept minus 19.7. All right, so that's just a binary variable, but you know what? If we have a variable that has many, many levels, the same process is still applied, right? So let's take a look at the neighborhood variable within the Ames data. Within the neighborhood variable, we actually have 28 different neighborhoods in our data, right? So we have a whole bunch of home sale prices, and these homes are scattered across 28 different neighborhoods, right? So we could actually use neighborhood as a predictor variable, and that would make sense because when we think about home values, typically neighborhood has a pretty big influence on what the values of a home are. So if we were to actually plot out the average sale price by neighborhood, we can see that there's quite a big difference between Stonebrook, Northridge Heights, and Green Hills compared to these neighborhoods down at the bottom of this plot, which is Briardale, Meadow Village, Old Town, Edwards, and so on. Okay, so we can see that there's a pretty big difference in the sale price, but we may actually want to model this. And we can do this by, let's run a simple linear regression model where sale price is simply a function of neighborhood. And now what we get is our model output where we have the intercept. So this is going to be for a reference neighborhood. In this case, the reference neighborhood is North Ames. That's actually the first level in the factor. And so now all these neighborhoods, right, the estimate here is the actual difference in the average sale price for that neighborhood compared to this neighborhood. So the intercept represents the average sale price for North Ames. That's $143,517. The average difference in the home sale price for homes in College Creek compared to North Ames is $57,007 more. Whereas the average home sale price for Old Town neighborhood is actually $19,609 less than the reference neighborhood, which is North Ames. Now, one thing to note is that when you have many levels like this, not all of the levels are going to be statistically different than the reference neighborhood, right? And so we could quickly look at this. Here, all I do is I take my model output and I'm going to range by p-value. So when I do this, we're going to do it in ascending order. And so what we actually see are those neighborhoods that have the smallest p-value. So all these neighborhoods are actually going to be statistically significant, or the difference in the average sale price compared to the reference neighborhood are going to be statistically significant. But if I were to go ahead now, I'm going to range and do descending order, we'll see that we have p-values that here's 0.9, 0.843, 0.738. So these are very large p-values, which means that likely coefficients are not statistically significant or statistically different than zero. So what that means is all these neighborhoods, we don't have very high confidence that their average sale price is truly different than the reference neighborhood of North Ames.